All right, guys, in this question, we're going to be looking at the photoelectric effect, talking about photons, energy, frequency, and how they're all related. So we're looking at two free response questions. In a photoelectron spectroscopy experiment, photons with a wavelength of 130 nanometers caused the ejection of 6s electrons from gold, but photons with a wavelength of 200 nanometers did not. A student claims this is because photons with a wavelength 200 nanometers are lower in energy than photons with a wavelength 130 nanometers. Do you agree or disagree with the student's claim? Justify your answer in terms of the energies of the photons. Before I answer this question, let's talk about the relationship between energy and wavelength. So I'm going to put this equation here. Energy is directly related to Planck's constant, and this is called frequency. All right, and we have another equation where frequency is inversely related to wavelength, where the speed of light divided by wavelength. So this is wavelength. We can use these two to do mathematical expressions, but we're also going to use it now to understand the direct relationship between energy, frequency, and wavelength. So energy is directly related to frequency. So if the frequency increases, energy will be increasing. And on this equation on the right, we can see that wavelength is inversely related to frequency, or frequency is inversely related to wavelength. So actually, the shorter or the smaller or the shorter the wavelength, we will have larger frequencies or bigger frequencies. Okay, which means if we're increasing the frequency, we're increasing the energy because those are directly related. Another way of thinking of it, if we're just going to go straight from wavelength to energy, the shorter the wavelength, the more energy they have. And that's because the frequency is inversely related to the wavelength and directly related to energy. So when we come back to our question, we're relating 130 nanometers wavelength versus a 200 nanometer wavelength. So the 130 nanometer wavelength is a shorter wavelength, which means it has a higher frequency, which means it has more energy, compared to the 200 nanometer wavelength, which is bigger, therefore smaller frequency, therefore less energy. So do we agree? Yes, we do agree with this student. When we want to justify, we will say because the 130 nanometer wavelength will have a higher frequency, it will then carry more energy. Or you can use it to compare. You'll say the 130 nanometer versus the 200 nanometer will have a higher frequency and therefore will have more energy. However you want to phrase it, as long as you put these ideas into place, you'll get the right answer. All right, looking at B, it's a similar question. We have photoelectron spectroscopy experiment, and this time we're looking at frequency. We have photons with a frequency of 1.2 times 10 to the 15th. Hz is hertz. It's just a unit of measure of frequency, and it causes the ejection of 5s electrons from silver. But photons with a frequency of 1.0 times 10 to the 15th hertz do not. A student claims this is because photon frequency with 1 times 10 to the negative 1 times 10 to the 15th hertz are higher in energy than photons with a frequency of 1.2 times 10 to the 15th. Do we agree or disagree with this student's claim and justify it? We're going to justify it the exact same way. And in this case, I'm going to disagree. I know that this student is incorrect. They have their idea backwards. Because 1 times 10 to the negative 10th hertz is a actually lower frequency than the 1.2 times 10 to the 15th, and frequency is directly related to energy. So I want to say that the 1.2 times 10 to the 15th hertz will produce more energy than 1.0 times 10 to the 15th hertz. And that's because I would go on to explain right here that hertz or frequency is directly related to energy. So if you have higher frequency, you have more energy. So this student just got it backwards. So we would disagree with this student's claim.